All right, hi guys. Welcome back. Looking at the wonderful world of logarithms you guys got introduced to in the last section. And now we're going to look at some of the properties of logarithms and how that might help us evaluate these or simplify them a little bit more. And so there's really 7 different properties that we're going to look at. And I think you're going to notice that because logarithms are tied in so closely to exponents and exponential functions, a lot of these are going to have some similarities to some of the exponent properties that you might already know. All right, but let's just go through some of these properties, and these are located on page 512 in your textbook if you want to see these. But let's just go through them. So again, b, m, and n here are positive numbers. B doesn't equal 1, and p and x are real numbers here. So if I have log base b of 1 always equals 0. Always, regardless of what b is. And then that's because anything to the 0 power equals 1. So if I have the log of to any base of 1, it always equals 0. Okay. And then kind of along those lines, but not really. Log base b of b will always equal 1. Again, think about switching this over. That simply says b to the first power is always b, regardless of what b is. Again, for b being a positive number. And kind of now along those lines, log base b of b to the x power will always be x. B to the x power always equals b to the x. And then kind of reversing that, if I have b raised to the log base b of x, I always get x. Again, b to the x power always equals b to the x. Again, so this is kind of that idea of inverse, that logarithms, these two kind of tie in that idea of logarithms and exponentials always undo each other. All right, so if I do the logarithmic of an exponential, I undo it. If I do an exponent of a logarithm, I undo what that originally did. Now, these next ones are going to be tied in really closely with your properties of exponents. So log base b of m times n is the log base b of m plus the log base b of n. And this basically says, hey, if I multiply two things with like bases, I can add their exponents. We have a property that says that. And then similarly along those lines, all right, if I have log base b of a quotient, then I can subtract those two things, log base b of n. So again, if I'm dividing two things with like exponents, or if I'm dividing two things with like bases, I can subtract their exponents. So similarly, I can subtract their logarithms. Okay, and then finally, the last one that we're going to look at is log base b of m to the p power is p times log base b of m. Okay. So again, if I've got logarithm of something to a power, I can take the logarithm and multiply it by p. And we're going to take a look at at how those apply here and exactly what we're going to do with these. And these all apply with natural logarithms as well. And so b here could be e. All right, so these I could have written each one of these with the natural logarithm as well. So what can we do with this? Well, if I'm asked to simplify, all right, so log base 10 of 10. Well, which one of these does that look like? That looks like this one right here. The log base 10 of 10, log base 10 of 10 just equals 1. Okay. Natural log of 1. Well, the logarithm of anything of 1 is always 0. The logarithm of 1 to any base is always 0. Okay, here 10 raised to this power. Okay, and again, I don't see a base there. So again, if I don't see a base, I'm assuming that to be a 10. All right, so my b's match up here. So that matches this property here, that if I have an exponent where the base of my exponent also matches the base of my logarithm, the answer is just x plus 8 here. This 10 and that logarithm kind of cancel each other out. What one does, the other one undoes. And then same thing here. This is e raised to the natural logarithm. So my answer is just 2x plus 5. Exponents and logarithms cancel each other out as long as their bases are the same. And natural logarithm has a base of e. We've got an exponent with a base of e. And then natural logarithm of e to the x plus 3 power, okay, simply says, all right, so let's see which one this agrees with. That looks like this one right here, because I'm doing the log base e, all right, so my answer is just going to be whatever my exponent was, so that simplifies just to x plus 3. And again, if you don't believe me, you can check this out. Do e raised to any power, all right, or pick a number for x. If x is 2, if you do the natural logarithm of e to the 5th power, it's always just going to equal 5. All right, whatever you plug in for e here, you can plug in for e there. Okay. All right, so we can use these to kind of simplify. All right. The other thing we can do, we can write logarithmic expressions as the sum of logarithms. All right, so here's what I'm talking about here. This is going to kind of apply back to this property here, that if I have a logarithm of a product, I can write that as 2 individual logarithms. All right, so for example, again, I'm assuming this is log base 10, but it really doesn't matter here. So I've got a product, so I can write that, so this would be like my m and this would be like my n. I can write that as the log of u squared plus the log of the square root of v. Okay, and that's a good start. Now I can also do this one, that if I have the logarithm of something to an exponent, I can bring that exponent down in front. All right, so this 2 can come down in front, so that's actually 2 times the log of u plus, all right, now wait a minute, the square root of v, I can write as v to the 1/2 power. So I can actually bring that 1/2 down in front, and I can write that as 1/2 log v. Okay, so this logarithm I can actually write as the sum of 2 simpler logarithms. So I don't have to do the logarithm of u squared, I just do the log of u. Once I figure out what u is and take that times 2, I can just do the log of v and multiply that by 1/2. Similar thing here, okay? So first I start with, I'm starting with a product, so I can write that as log base b of x to the 4th plus log base b of the cube root of y. And now that exponent I can bring down in front, so it's 4 times the log base b of x. And the cube root of y, again, that's y to the 1st, I can write as y to the 1/3 power. So I can bring that 1/3 down in front and write it as 1/3 times the log base b of y. I can take it down to just simple logarithms without all those exponents and radicals. And then I can also go the other way, all right, writing a sum of logarithms as a single logarithmic expression. So the first thing I notice here, if I've got 2 log 3, I can take that 2 up in front. This is just basically reversing what we just did. And same thing here, I can take that 4 in front, that's the log of u to the 4th. And now I can write the sum of 2 logarithms as one logarithm, the log of 3 squared u to the 4th. Or you might write that as the log of 9 u to the 4th. I'd take either one of those 2 answers. Similar thing here. I can bring the 2 up, so that's the natural log of x squared plus the natural log of y cubed, which now I can write the sum of 2 natural logs as a product of natural log of x squared y cubed. So these 2 are just basically going back and forth between, hey, can I write it as a single logarithm? Can I write it as the sum of 2 individual logarithms? Getting used to those logarithmic properties. I can also do it with differences, okay? So the natural log of x squared divided by y cubed, I can write that as the natural log of x squared minus the natural log of y cubed. And then I can bring those exponents down in front. 2 times the natural log of x minus 3 times the natural log of y. Same thing here. This would be natural log of a to the 4th minus the natural log of b to the 5th. And then I can bring that 4 down in front. It's 4 times the natural log of a minus, bring that 5 down in front, 5 times the natural log of b. That should be a B, not a 5. So part of your homework tonight is just getting used to using those properties of logarithms. And again, I can also do that backwards. So I can bring the 2/3 up. So this would be the natural log of x to the 2/3 power minus the natural log of y to the 1/2 power. Now I can rewrite this. X to the 2/3 is the cube root of x squared, and y to the 1/2 is the square root of y. And then I want to write that as a single logarithm, so I can write that as the natural log of the cube root of x squared divided by the square root of y. Similar thing here. All right, bring the 1/2 up, so that becomes log of a to the 1/2 power minus log of b to the 3rd power. A to the 1/2 power is just the square root of a, so that's log of the square root of a minus the log of b cubed. Not much I can do there. I don't have a fractional exponent or anything. And now a quotient, or a subtraction problem I can write as a quotient, so I can write this as a single logarithm. Log of the square root of a over b cubed. And then just kind of combining this all together, combining these into a single logarithm. So I've got 3 different logarithms. I'd love to write it just as a single one. So log base b of x cubed. Not much I can do there, so let's just leave that as log base b of 2x plus 1 minus log base b of 4 to the 2nd. I'm adding together 2 logarithms, so I can write that as a single logarithm if I multiply those 2 things. So it's log base b of x cubed times 2x plus 1 minus log base b, and I'm just going to write that as 16 because that's what 4 squared is. Now I'm subtracting 2 logarithms, means I can do that as one single logarithm, log base b of a quotient, x cubed 2x plus 1 over 16. I took that big, long, complicated thing and made it a little less complicated, at least written as a single log. Similar thing here, I got a natural log, log base e. So again, take the 2 up, so that's the natural log of x squared minus the natural log of 3y plus, need to get better mechanical pencils, natural log of z cubed. So I am subtracting these. That means I can write that as one natural log if I do a quotient, x squared over 3y plus the natural log of z cubed. And now a sum I can write as a single logarithm if I multiply. There it is, natural log of x squared z cubed over 3y. So some of this, again, I get kind of tedious, but just getting used to writing these or using these properties of logarithms. Okay. Now, one last thing I want to look at, and this one actually is going to be useful, and we'll see why here in a minute. But it's a change of base formula. Okay, and we'll look at why we might want to change the base. So it says for any logarithmic bases a and b and any positive number a, the change of base formula basically says that the log base b of m is equal to the log base a of m divided by the log base a of b. So what this does for us is it's especially useful if we make A the common logarithm, because I can do that on my calculator, or the natural logarithm, because I can do that on my calculator. So for example, it says evaluate 4 or log base 4 of 17. Really what we're asking here is 4 to what power equals 17? And I don't know what it is. It's a little bit bigger than 2, but my calculator can't do that. But using this change of base says, all right, I'm gonna use A. I'm gonna use A as 10. All right, because I know that's what my calculator can do. So what the change of base formula allows you to do is I can rewrite the log base 4 of 17. Again, M here is 17, B is 4. All right, and I'm going to make A 10. And I'm choosing 10 simply because that's what my calculator can do. So what I can do is log base 10 of 17 divided by log base 10 of 4. I can take this base that I can't do on my calculator and change it into something that I can do. And so now I can simply do, again, log base 10, that's what my calculator does, all right? So I can do the log of 17, make sure you close your parentheses, divided by the log of 4. And it does say 4 decimal places, so this is approximately 2.0437, which is kind of what I thought. I said it was going to be, something a little bit bigger than 2, because 4 to the second power would give me 16. Okay, but what this allows me to do is evaluate these logarithms using this change of base formula. Now, just real quick, I said we could also make, you could also do this as a natural log. So because my calculator do that, notice if I do the natural log of 17 divided by the natural log of 4, I get that same answer. Okay, so it doesn't matter what you make A. A lot of times we make A, not a lot of times, all the time. Make A either 10 or E, because that's what our calculators can do, and then it'll let you evaluate these. Okay, so log base 7 to 34, again, helps me to see what I'm trying to do here. 7 to what power gives me 34? Something less than 2, because 7 to the second power would be 49. But what I can do, you can do natural. I'm going to do the natural log this time. The natural log of 34 divided by the natural log of 7. And if I do the natural log of 34, make sure you close those parentheses, and divide it by the natural log of 7, I get to 4 decimal places 1.8122 if I go 4 decimal places. Okay. So the change of base formula, again, it lets us evaluate these logarithms that before we really couldn't do by getting it either in the common log or the natural log that our calculators can calculate. Okay, well, hopefully this helps. If you have any questions, take a look at these homework questions. If you have any issues with these, please get a hold of me some way. I'll be more than happy to take a look at some of them. All right, take care, guys.